Just a moment. I hope you hear me well, and thank you very much for joining us. I would like in the beginning first to thank to Professor Dragan Huterer for his goodwill and our ability to give a talk today. In the beginning, I would like to explain a few reasons, motivation for today's talk. Namely, SEENET-MTP has organized in 2022 during the COVID-19 pandemic a series of lectures that you can find on our web page. The second reason is to help to the students who are preparing for our next school in the CERN SEENET ICTP PhD program, which will take place in Institute for Nuclear Research in Magurele, Bucharest. I hope you see the poster. So the school will start on the working days. First working day will be 1st of July, and it will take till 6th of July. After that, we will continue with the workshop on high energy physics. And the third reason is that this is the first year we are not granted by ICTP for the mobility program. So this lecture and the lecture that will be given for another school lecture, it is Professor Raul Jimenez from Barcelona, will be preparation for the students. In other hand, it is not just for the students, for all researchers in the network, to be introduced by Professor Huterer about a very active and let's say hot topic in high energy physics, in cosmology. It's related to the dark energy. So just a few words about today's talk. I will remind you that today we will have a lecture titled Cosmological Results from Dark Energy Spectroscopic Instruments, 3-year analysis. A few words about our today lecturer, Professor Dragan Huterer. He was born in 70s in Sarajevo, Bosnia and Herzegovina, at that time Republic of former Yugoslavia. After he completed his high-level school, he then continued studying at MIT in USA, then continue his education and PhD in Chicago, and after several postdocs, he now is a full professor at University of Michigan. He's very active researcher with a lot of scientific results, several books, and in the last few years, he's very much involved in the dark energy survey in cooperation with DESI, and he is for sure one of the leading researchers and one of the best person for introducing us with this very active part of research. So I would like to thank Dragan very much for his accepting our invitation. He also contributed in 2018 as a invited lecturer at the workshop and the school that we organized in Niš, Serbia in 2018, and again for the school we will have in Bucharest. So I hope I didn't took too much time of that. Dragan, please, you can start with your lecture. The lecture will be recorded, and some people who were not able today to follow it will have a chance after that. After that, you will have a possibility for several questions. Thank you.
Thank you, Goran. Thanks very much. Let me see if this sharing works. So you should be seeing my screen now. Thank you very much. It's a pleasure to talk about this. I hope you can see the screen and you can all hear me. But I am Dragan Huterer, and I will talk. This is not like really like introductory talk in cosmology. Reviews a bit of a background, and I'd like to talk about recent developments in our understanding of dark energy and some of the most recent and best measurements. So this is the picture of actual galaxies from the DESI survey. I'm going to explain a little bit about the survey later, and maybe hopefully you can see my cursor. If not, it's okay. But we sit in the center and we are looking out, and all of these are real galaxies. Every point is a galaxy with a fake color, but real position. And this is a tiny fraction of galaxies that were observed in the DESI survey. So I'll explain how we use this distribution of galaxies to understand dark energy. But to start off a little bit, here's a picture from my former student, Noah Weaverdick, starting at the Big Bang to the present day on the right. Lots of things happened, but three of the most important epochs, arguably, are the early universe with an inflationary period right after the Big Bang, and then much, much later in the history of the universe when dark matter and dark energy dominate. And for each one of those things, there are some questions. For dark matter, it is what is the dark matter particle and what is its interactions and decay modes. For dark energy, I'm going to talk about that, is simply what's behind the accelerated expansion. Why is the universe expanding faster and faster? And for inflation, there's a range of questions. We do know a lot about inflation, but we'd still like to know more details about the physical processes that took place moments after the Big Bang. Now, for dark matter, just to give a little bit of introduction, probably many of you have seen this before. These are some of the most familiar pictures. These are drawings by another one of my former students, Jesse Muir. So Fritz Zwicky found evidence for dunkle Materie, as he said in German in 1933. So dark matter is actually this year 92 years old. It's older than most people. And he saw evidence, and it was only up until the 1970s when Vera Rubin and collaborators, they measured speeds of stars moving around galaxies and found that those speeds are larger than would be expected if you only had visible matter. Later on, you again see some of the best known pictures in cosmology. This is the kind of visual evidence, so to speak, for dark matter. So people have reconstructed the density profile. So the y-axis here is surface density as a function of xy coordinates in the sky. And the individual peaks are galaxies, but this hill is really the smooth dark matter distribution. This is dark matter around the cluster of galaxies. And similarly, this very famous bullet cluster where two clusters collided several hundred million years ago. And because of this collision, the baryons have left this bullet-shaped shock feature. So this is where the baryons are the color given by X-ray light. But then the clincher is that you can reconstruct the mass from gravitational lensing, and the mass, the green contours, does not agree where the baryons are. So this is showing that mass are actually, the dark matter is offset from the baryons after this collision. And this is another piece of evidence for dark matter. So those are all pretty compelling. But by far the most compelling evidence for dark matter is not so visual in nature. So it's not any picture. It is a picture, but not so obvious. It's really the cosmic microwave background, whose hot and cold spots, if you work out their distribution given by this angular power spectrum, agree really well with a model where dark matter, this is the amount of dark matter to critical multiplied by little h squared is about 1/2. So that number, this is about half of the fraction of dark matter. It's 11.9%. So this number is very far away from zero. This number is actually almost 100 sigma away from zero. So this is, even though it's not so visual, this is the strongest evidence for dark matter to date, that without dark matter, this angular power spectrum would look completely different. It would not agree with observations. And for dark energy, which I'm going to talk about next, really this is one slide that describes what the whole talk could be about. Type 1a supernovae that have been known for a long time. This is, you can see type 1a supernova going off in this galaxy, and its luminosity is some fraction of that galaxy. It's a very bright object. They are nearly standard candles, and if you look at their light as a function of time, in fact, you can correct them for one parameter family of curves, and after that correction, they become very good standard candles. And that means that their luminosity is the same, and now you are in a very good position, because if the luminosity of each supernova is the same and you measure flux, then you get distance, you don't quite get the absolute distance, you get the relative distances between supernovae because you don't know the luminosity, you just know it's the same. And so this plot I like very much. This is both a popular and a technical plot at the same time. On the y-axis is the distance modulus, which is the logarithm of a distance, basically, as a function of redshift. And you can see that this is real data from a few years ago. Each data point is about 20 supernovae. So these are supernovae binned in redshift. They're binned together, so easier viewing. So each data point is about 20 objects. And you can see sample cosmologies with matter only that have open, flat, and closed geometry. None of them agree with the data. Rather, what agrees with the data is a cosmological model where a universe accelerates now and decelerated in the past. So that's a model where universe is speeding up now. And so the cartoon picture of the universe favored by supernova data, sorry, so this is like hard distances. So the cartoon picture is, universe is expanding slower and slower, and then very late, right about now in the history of the universe, just a few billion years ago, it starts to expand faster and faster. That's a very surprising discovery made in the 1990s. And I was a graduate student at the time. I thought maybe we'll, any year now we'll understand this, but it turns out this is one of the biggest and most puzzling discoveries made in cosmology. It led to the makeup of the universe that's very familiar, I think, to everyone on this call, with about 3/4 of energy density in dark energy, and about a quarter in a matter, mostly dark matter, and some baryons, and actually very small fraction is stars. So most of the universe energy density is in dark energy. And these constraints you may have seen, these are constraints on the matter density on the x-axis relative to critical, dark energy density on the y-axis. The fact that supernovae above zero in this graph is the discovery of dark energy. So dark energy density, represented by cosmological constant, is the vertical, and it's favored to be greater than zero, in fact 0.7, and matter density is 0.3. You can also see that other cosmological probes, in particular combination of baryon acoustic oscillations and the cosmic microwave background, independently together, they point to the same model. Now, BAO is the probe I'm going to talk about later in this talk. So I'm going to explain the BAO, and this is just the microwave background constraint. You can also allow equation of state of dark energy, which is P over rho, to vary as a free parameter. Now, P over rho, the W, is -1 for lambda CDM cosmological model. So in the left panel, it was assumed that W is -1. In the right panel, W is allowed to vary. And constraints on this parameter have shrunk around the value of -1. They become smaller and smaller, and have shrunk around this value over the past 20 years. Near the end of the talk, I'll show very exciting results where W is described not just by one parameter like here, but by two parameters. And they indicate departure away from this cosmological constant case. But for the moment, everything in the past 20 years has been very close to, was in agreement with W of -1. So W is P over rho -1. That's cosmological constant. There are two mysteries coming with dark energy. They are kind of all-time big questions. And the smaller one of the two is the coincidence problem. So this is the energy density of things as a function of time. We are here when dark energy to dark matter is about 2 to 1. So they're very comparable. But dark energy is approximately constant in time. It's exactly constant in time, the energy density when W is -1. And matter falls off with time, and radiation falls off even faster. So if we woke up in the past and try to see what's going on, dark matter or even radiation will be dominant. In the future, presumably dark energy will be completely dominant. So why do we happen to just live in an era when the two are comparable? This is a coincidence problem. And it's hard to put a measure on how surprising this is, because it's one of those things you say, guess what happened to me today? I went outside and I saw something. I saw all the people have a red t-shirt or something. I saw 3 cars of some make. So it's hard to tell how unusual that is. Nevertheless, this has motivated a lot of models that were designed in order to make dark energy and matter be comparable today. So this was a big motivation for model building. It's a coincidence problem. That's the first one of the two problems. The second one of the two is one of the most famous unsolved problems in physics. Turns out that vacuum energy of the vacuum, would be perfectly good dark energy, and you can calculate rho of the vacuum energy using standard calculation from quantum field theory, adding up 0-point energies of a quantum harmonic oscillator over k space. That expression violently diverges with K, but if you cut it off at scales where we think it should be cut off, you get the answer much, much, much bigger than the measured amount. So this is energy density is units of EV to the fourth. And the measured amount is so much smaller than these other, that this is really a great puzzle. It could be vacuum energy, except somehow it has to be much smaller than measured. This problem of diverging of vacuum energy has been known to Wolfgang Pauli almost 100 years ago. It's one of the big unsolved problems in particle physics, and a lot of physicists think that a major new understanding of some aspect of physics will be required to understand this problem. So there has been no progress in understanding why vacuum energy, number one, why is it so large? And number two, if it's not zero, why is it such small value? So in here, concluding this introduction, it's fair to say that evidence for dark energy is excellent. It's been established to more than 100 sigma evidence. So for sure, there's something like dark energy out there. All the measurements are in agreement with dark energy. And they're getting better, as I'll show now. And theory is far behind. Theory in explaining dark energy is far behind. So that was my introduction, mostly covering dark energy. Meanwhile, there was another development. First of all, because maybe not everyone on the call is a cosmologist, let me remind you about Hubble constant. This is in expanding space. Objects that are farther away from you are expanding, receding faster away from you. This was discovered by Edwin Hubble almost exactly 100 years ago. This is his plot from 1928 paper. The funny thing about this plot is it's true, it's a line, but the slope of the line is actually 7 or 8 times too big. The slope should be more like where my cursor is going. The slope should be this big. So the data points and the slope are completely wrong. What's correct about it is it's a line. And he discovered that in the modern value is much smaller slope. It's about 70 kilometers per second per megaparsec. This was established in the 1990s. Now, there are some recent measurements of this, and one kind of measurement is from the so-called distance ladder, direct measurements in the local universe that give 73. Another set of measurements is cosmological measurements from, say, microwave background that give 67. Now, both of those numbers look like 70, except when you look at the error bars are very small. And in fact, these numbers are very significantly different from each other. And in fact, they are different at the 5 sigma level now. So if you add these errors in quadrature, you'll see you get more than 5 sigma than this. Both of these measurements are very firmly established. It can be 2 numbers. It's like the speed of light. It has to be 1 number. If you get 2 numbers, either it's a different cosmological model or some mistake has been made. And so in my opinion, this has been the most exciting discovery in cosmology in the past 10 years, this development of the Hubble tension, that these 2 numbers simply disagree. I'm going to show in a few moments a set of measurements of DESI that agree with this number and disagree with this number. But anyway, there have been, I think, over 1,000 papers now discussing this problem and trying to find theoretical solutions and maybe even solutions in data analysis, although the data analysis is a very firmly established one too. So that's a Hubble tension, very, very exciting development. So these are some of the best known telescopes built, either ongoing or planned, to measure dark energy and also motivated by Hubble tension now. And these are some of the most familiar names from the ground. You have KIDS and DES that have going on or completed, and Hubble Hyper-Supreme that's ongoing. And then this is a really big one, LSST survey on a Vera Rubin telescope. And then in space, some of the best known names, Euclid Space Telescope that's operating, the Roman Space Telescope that might be launched in a couple of years. And then here, I'm going to pay attention and talk about DESI, Dark Energy Spectroscopic Instrument. I will explain what DESI is. I will show some really exciting results that we got and where we're going with that. So DESI is placed on a telescope called Mayal telescope. This is a telescope, this big building, on Kitt Peak in Arizona. It's a collaboration of 900 scientists from 72 institutions in the United States, funded by the Department of Energy. And I'm going to talk about some instrumentation, but it's operating extremely well. On a good night, it gets up to 100,000 spectra. And this is really a shocking discovery. It was before my time when an astronomer goes to the mountain and gets a big coat and collects a spectrum. But in my time as a cosmologist, a student, At some point, Sloan Digital Sky Survey had 1 million spectra, and that was a big development. And this is 100,000 in a night. So if you have 10 good nights, you get 1 million. So this is really a machine for getting spectra. Now, I'm a theorist, and I don't know much about observations at all. And my observer colleagues tell me the following. The telescope is okay. It's an okay telescope. It's not the world's best telescope. But what is really remarkable about this is instrumentation that was put on the telescope. And before I talk about that, let me just mention that we cosmologists treat particles. Galaxies are our test particles. So each galaxy is like a test particle to us. So that's a kind of an interesting thought. With 100 or 1,000 galaxies, you can't do much, but with millions of galaxies, you can study the structure in 3 dimensions, and you can learn about cosmological parameters. So I did mention the instrumentation is special. So this is a Mayal telescope from inside. The telescope was built in the same year I was born. Goran very kindly said 1970s, 1972. And the telescope was built in 72, so it's an old telescope. But instrumentation is new, and these spectrographs are, operating well, impressive. But the most important piece, arguably, has been constructed at University of Michigan by my colleague Greg Tarle. And there's going to be a little movie running here in the corner. So that has to do with these fiber positioners. They're little sticks. They're the size of a pencil. And you can see them operating here in this movie. And each one points at a galaxy. So you have to pre-select those galaxies. You have to know ahead of time what galaxies to point to. Then each one points to a galaxy, 5,000 of them. You spend half an hour, you collect light, you take 5,000 spectra, and then they go bzzz, they move to new positions. Then again, you take 5,000 spectra, bzzz, another 5,000. They make sure they don't collide with each other. They move around just like you see. And they collect 5,000 by 5,000. You get up to 100,000 galaxies in one night. So these fiber positioners, they were built 3 doors down from my office where I sit right now at University of Michigan. So they were built here. And that is really the key piece of instrumentation for DESI. And so with those positioners, we take spectra of galaxies. So by spectrum, you get 3rd dimension. What kind of galaxies? Well, different kinds of galaxies. They have these not very inspiring names that are historical. At nearby redshifts, they're called bright galaxies. So there's a bright galaxy survey, so BGS. A little bit farther away, so-called luminous red galaxies. These are older and more elliptical galaxies that have a certain feature, spectroscopic feature that can be found. And then a little bit further away, emission line galaxies, ELGs. So there's young star-forming galaxies. And both LRGs and ELGs, we split in few redshift bins. So you think about a few bins in redshift. And then at largest distances, we have quasars, and then also these so-called Lyman alpha features, which are hydrogen absorption features on the line of sight to quasars. So we have quasars as objects, and also Lyman alpha features along the line of sight to those quasars. So there's a little bit of apples and oranges that we have here, different kinds of galaxies and quasars. But with that, we map out a big chunk of cosmic history with many tens of millions of objects. This is a semi-popular picture, and if you are not a cosmologist, this picture might be quite useful. This is showing just how a single spectrum redshifts. So this is a spectrum with some spectral features as a function of wavelength. Looking back in cosmic time, so you can see that certain spectral feature redshifts. It shifts in wavelength as you go farther and farther back in time. So with Bright Galaxy Survey, we look certain distance back in time, but LRGs and ELGs, eventually quasars and Lyman alpha, you look way back in time. And so by recognizing that spectral feature and measuring at what wavelength you observe it, you can find out the redshift. That's how we measure redshifts. So that really is essential part of DESI. It gives us that 3rd dimension in the sky. It gives us the redshift by observing the spectral feature. So that was the background on DESI. Now I move on to discussing data, and then I will discuss cosmological results, and then I will wrap up. So the data, so I mentioned these kinds of objects, and you can see the numbers. The number is in the millions. And I'm going to discuss the so-called data release 2, DR2 that was released, papers and analysis were released in March this year. And you can see a total of 15 million objects. We have more objects than that, but these are just the ones that are used in the analysis. And now this is going to go show you, so this is coverage on the sky. This is galactic plane. We mostly observe in the north because this is in Arizona. Kitt Peak is in Arizona in United States, but we have a little bit of southern coverage. And this is coverage in DR1. So the red color is this, the color is how many times in the sky did you cover? Ideally, you cover a spot 7 times, but some spots are less covered. So this is in DR1, and if I click my button here, this is now going to become more red. And this is the coverage in DR2. So you can see in DR2, we started to fill out these areas that are planned. And we covered a lot of the area, and really massive improvement in both the number of galaxies and in how many times we covered certain areas. So now, before I discuss cosmological results, I will explain what we measure. And this is a little bit more technical part of the talk, just a tiny bit more technical. It is helpful to have some cosmology background here, but if not, I will try to explain. So I'm going to explain the so-called baryon acoustic oscillations, or BAO. This is a feature in galaxy clustering that's been well known, that's been first recognized also actually in 1972 by Sunaev and Zoldovich, two Russian famous cosmologists. So DESI collaboration published hundreds of papers. There are hundreds of papers out there, but there is one key thing that we are doing. The number one thing is this BAO. So BAO is number one. Everything else is number 2, 3, 4, etc. This is the number one science we are after. So I'm going to explain what BAO is. So this is to start with, and I'm borrowing here a few pictures from my cosmology textbook. This is the matter power spectrum. So this is the key function in cosmology. It's a little bit of a technical thing. It's a Fourier transform of the correlation function in real space. It's a power spectrum, P of K. It's a power law from inflation. It's K to the N. Inflation predicts it's a power law. But then there are many other features. There's this turnover feature, which is due to the fact that universe goes from radiation dominated to matter dominated 50,000 years after the Big Bang. So this turnover feature is a big thing. And then at smaller scales, this is a linear power spectrum. Then there's non-linear part. Sorry about that. Okay, I hope I'm back with my slide. So this is a non-linear part. And nonlinear has to be simulated in simulations. And there are lots of things, but if you look, there are small wiggles in the black curve. In fact, they are not even visible in the dashed curve, which is a fit without wiggles. So these small wiggles are the BAOs. And so if I take that and I blow up these wiggles, I get this. So this is the Wuzu's wiggles blown up a little bit. And this is some older data. This is not DESI data. And multiple wiggles in Fourier space correspond to one wiggle in configuration space. So this is configuration space. So this is real space. This is R squared times psi of R. Psi of R is a 2-point correlation function. You see there's a bump at a distance about 100 h inverse megaparsecs. Little h is Hubble constant in units of 100. So little h is about 0.7. So 100 h inverse megaparsecs is about 150. Actually moving megaparsecs, but we carry this h inverse with us. So this bump corresponds to the small axis for clustering. So there's a small probability for having a pair, another galaxy near you, 100 h inverse megaparsecs away. Now the big question is, why is there this axis? Why there are those wiggles, and why is there this single BAO feature? And the reason has to do with the sound wave. So when people say sound, I think of it as the speed of propagation of fluctuations, of density fluctuations. So sound propagates from the Big Bang to the present day, but the speed of sound is c speed of light divided by square root of 3 for the most part, up until recombination. At this time, at recombination, speed of sound drops like a rock. That's when photons and baryons are not coupled anymore. So speed of the sound goes from c divided by square root of 3 to a very small value, like a few kilometers per second. So most of the distance that sound travels happens between Big Bang and recombination. And this is the only formula I think I'm going to show today. This is a formula for the so-called sound horizon. Sound horizon is the distance that sound can travel between Big Bang and today. The speed of sound in the early universe is, as I said, c divided by square root of 3 times, this is integral d time. Integral d time has a correction due to baryons. But basically, this is a formula you can put on a computer, and it's one line of code in your favorite computer language. and you can evaluate this formula for, the universe of dark matter and dark energy, you'll get about 150 megaparsecs. So this is the sun horizon. That's the key feature that imprints this excess probability. So when you look at the sky doesn't look exactly like this. But if you imagine sky looking like this and you look at one galaxy and there's less and less and less probability of finding a galaxy, 108 inverse, about 150 megaparsecs away, there's this ring. This is like an excess probability for having a pair. So people say we measure the standard ruler. It's not actually any physical ruler. It's this feature in the clustering signal that we measure. That's what we refer to standard ruler. So literally, and this is a really key point about the BAO, we sit here on Earth and we measure this ruler, which is not like a stick. It's the feature in clustering at the distance to those galaxies. So because we measure angles in astronomy, typically we measure the ratio of the sun horizon to the distance to those galaxies, or vice versa, we measure distance to sun horizon ratio. So this is a key point of BAO. We measure this ratio of distance to those galaxies divided by the sun horizon, where sun horizon is typically pretty well known from the cosmological model. And so this comes out of the box. This is what BAO measure. And from that formula, you saw that the formula is exact. There's no theory error. So this is like really very firm, physically very firm kind of measurement. And so there's just one detail here that we actually galaxies can be transverse. So I'm going to again show with a cursor. Galaxies can be like this, transverse, or can be along the line of sight, like so. And if they're in between, if the pair of galaxies like so, that we can project to either transverse or parallel. So we measure two kinds of distances. We measure this d over rd for transverse positions, and we measure the same quantity for line of sight. Okay, so just to give you an idea, this is a kind of a data compression. So we measure millions and millions of galaxies. From them, we measure clustering. So we extract this BAO feature. And from this BAO feature, we get this ratio, d over rd. We bin our galaxies in 7 redshift bins. So it sounds like we would have 7 of these measurements, but actually we have 14 measurements because we have one each. At each redshift, we have this measurement for transverse and to the parallel of the line of sight. So, okay, as I mentioned, this was a little bit more technical part, but it was necessary to explain what the BAO is. And if you missed all that, it has to do with this standard ruler. And really, the quantity we measure is the ratio of a distance to some galaxies, which contains information about dark energy, to the sun horizon, which doesn't have information about dark energy, but requires a little bit of prior to know it. This is my group at University of Michigan, recent picture, not quite up to date. Everybody is working on some kind of DESI. I wanted to highlight especially postdoc Wendert Andrade. He played a big role in this effort of a 1,000-person collaboration. He was in charge of so-called blinding, hiding the answer before we are done with analysis, and he also coordinated year-3 analysis. He's here at Michigan. Johannes Lange, another postdoc who is now professor in Washington, D.C., and you can see some students who work on this. Okay, so I'm going to show now cosmological results from DR2, that is year 3. 3 years of observations or data release 2 analysis. It mainly comes from this key paper. The DR1 paper, which we published in 2024, was, according to Inspire, the most cited paper in astronomy or particle physics in the world in 2024. It got a lot of publicity, and its dark energy results. And the results from this paper, from these new results, also confirm what we found in DR1 and improve quite a bit upon those cosmological constraints. So I'm just going to show the very, very highlights here. There are lots of things to talk about. I'll just show 3 key results, and then I'm done. So first of all, let me show the measurements. So let me show what's explained here, what's shown here. This is that ratio of the distance. Oops, sorry about that. The ratio of the distance to sun horizon. Except here, that's what we measure by DESI. I divided by the best fit d over rd, so that we are not looking at weird numbers. So 1 here means best fit in the lambda CDM model, and this is the ratio. And so these 3 plots are 3 different. So the 2 plots on the below are perpendicular and parallel BAO. So this is the transverse BAO I mentioned in line of sight. And then the isotropic is not independent. You can get isotropic by basically taking a product of perpendicular parallel. So maybe let's just look at these two plots. So the flat line, as I said, is lambda CDM best fit. The filled symbols are points, measurements from DR2, and the open symbols are just previous year's measurements. So you can see the error bars are better. And then the dashed curve and the error bar is the best fit from lambda CDM model, so from Planck measurements. So this is best measurements from Planck. And they are not going to be exactly the same as, you know, best fit model from DESI. So best fit model for DESI is, so there should be 14 data points here, 7 redshift bins, and in each we have perpendicular and parallel BAO. So it's a massive form of data compression. You start with gazillion photons, then you have 15 million galaxies, then you compress down to power spectrum with several hundred numbers, and then you further compress to 14 numbers, 7 numbers here and 7 numbers here, and a 14 by 14 covariance matrix. And that compressed thing is what we constrain with. So out of the box, this is again a bit of a technical point, but in lambda CDM model, we measure omega matter, which is the amount of matter in the universe. It's 1 minus omega dark energy. And then this funny combination of the product of the sound horizon and the Hubble constant. So the plane is omega matter versus H naught RD. So this parameter is not familiar. This parameter should be familiar. It's the amount of matter. But what I want to show is how degeneracy gets broken as you go from quasars to bright galaxies, which are different redshift, so they have different degeneracy direction, to luminous red galaxy in redshift bin 1 and LRGs in redshift bin 2, Lyman alpha forest features, emission line galaxies. This is a combination of emission line galaxies and luminous red galaxies. These are not from the same, but this is LRG cross with ELG from another bin. And then when you combine them all, you get this very, very tight contour. So you can see really, I would say, spectacular degeneracy breaking in this plane when different tracers, these different kinds of galaxies combined, even though each alone is not very constraining, in combination, they are very, very constraining. And we get constraint on omega matter of 3% of about 0.3, so 30% omega matter with a small error bar. And then we get this combination of Hubble parameter and the sound horizon. So now I'm going to show 3 key results, and then I will wrap up. The first result beyond this is going to be constraints on the Hubble constant. So notice we get product of the Hubble constant in sound horizon. So we need to solve for the sound horizon to get H naught. And that prior that we need is given by Big Bang nucleosynthesis, BBN, abundance of lightest elements in the universe compared to the standard prediction, gives you the amount of baryons, which in turn you can use to solve for the Hubble constant. And we get, with this BBN prior, we get Hubble constant of 68.5 plus minus a small number. So this agrees with the CMB constraints of 67.5 and disagrees with local measurements by Schu's collaboration of 73. And we disagree with Schu's at 4.5 sigma. This is as expected. We fully expected we were going to agree with the CMB and disagree with Schu's. What's new here is we have a 4.5 sigma evidence for disagreement with Schu's without CMB. So that, you know, famous disagreement isn't just CMB with Schu's, it's all these global measurement. This is DESI plus BBN with no cosmic microwave background, gives a value that agrees with CMB, obviously, and is very different from the Schu's measurement. So that's a featured result number 1, constraints on the Hubble constant, which are very precise and came out really as expected. And these constraints are more surprising as this. So this is not, there's no surprise here. Number 2 result has to do with the neutrino masses. Now, cosmology measures the sum of the neutrino masses, but oscillation experiments measure the sum differences of squares of neutrino masses, so delta m squared, which from solar and atmospheric oscillations are these 2 numbers. Now, there are infinitely many triplets of m1 plus m2 plus m3, or infinitely many values you can write based on the solar atmospheric measurements. But if you assume for the moment that the lightest mass eigenstate is 0, the least you can get for the masses, The least it can be is 0.06 eV in the normal hierarchy, or 0.10 eV or so in the inverted hierarchy. So given the oscillation experiments and given standard model of particle physics, you have to get this much or more. Like 0.06 is absolute minimal value you can have for the sum of the neutrino masses, and we are sensitive to the sum of the neutrino masses. Now, if you're like me, you think of neutrinos of very fast relativistic particles. So it might come to surprise to you if I tell you that neutrinos are actually very non-relativistic today. They're non-relativistic. And the reason they're non-relativistic is, even though they're light, they are much heavier than the temperature of the universe today, because the temperature of the universe is very old and very cold today. So even though you think of neutrinos as this very fast moving close to the speed of light relativistic particles, they're actually non-relativistic today. So they contribute to expansion history just like matter. They behave like matter today. Actually, since the redshift of 100, neutrinos have behaved like matter. So we, in BAO, constrain neutrinos only indirectly. This is the plane of neutrino mass versus omega matter. And here we really rely on CMB measurement. So this is a CMB constraint that's degenerate between these two parameters. In DESI, what we do is BAO is not sensitive to neutrino mass sum, but we measure the amount of matter. So we are sensitive to omega matter. So you combine the CMB result with a vertical band in this plane, which is a measurement from DESI, so this plane. And because we favor a slightly lower value of omega matter than CMB, we cut off our vertical band, cuts off these contours at a very, very sharp angle, and we get a very, very tight limit. At 95%, we get less than 0.064 electron volts. In lambda CDM, in models beyond lambda CDM, this is relaxed, but still fairly tight. So people have puzzled a little bit, why and how do we get this number? It is what we get. I have a little bit more explanation here. So this is now showing posteriors likelihoods as a function of some of the neutrino masses. And these are those absolute, these are predictions from the normal standard model of physics for normal and inverted hierarchy. In either way, you have to be greater than 0.06. And here you see we push against 0. So our upper limit is actually about 0.06. Now, we still don't rule out these hierarchies. We are still significant to them. And so some papers out there, they say we find unphysical. Nothing here is unphysical. We have greater, we assume greater than 0. It's just our likelihood is pinned against the 0 value, but we are not ruling out anything so far. Nevertheless, we have a whole new supporting paper led by this postdoc where we discuss, put more detail. So I can answer any questions about this. Everything is in order. It is just happened that we, in combination with the CMB, favor very low values of neutrino mass, and so with better data, we might be ruling out some of these hierarchies. So we'll see how that evolves. Now, interestingly, this neutrino constraint it got some publicity, not a ton of publicity, but what got a lot of publicity is my third and large featured result, which is constraints on dark energy. Now, remember the equation of state P over rho. We now generalize that and use this very popular model. I can answer if anyone wondering about this model. It's a very flexible model with two parameters, W0, WA, where dark energy equation of state goes from W0 to W0 plus WA as you go from the Big Bang to the present day. So this allows both variation in value of W as well as evolution in time of the dark energy equation of state. And so therefore, we are going to be looking at the W0, WA plane. And that plane is very hard to constrain. You can just trust me on that because I worked in my PhD was basically on understanding how constraints here work. So lambda CDM model is represented with W0 minus 1 and WA of 0. So this is a standard cosmological model. And constraints from DESI DR1 and DR2 are shown here. And just the fact that DESI constraints give you something is very interesting because this is a very challenging plane to constrain. You can see we pull a little bit at less than 2 sigma away from the lambda CDM model. But now we combine with the CMB data, and DESI plus CMB is now 3 sigma away. So these two contours, these pink contours in DR2 are 3 sigma away from the standard model. And further, we can combine with type 1a supernova data. Now with type 1a supernova, there are 3 major data sets One is called Pantheon Plus, and then Union-3 and Dark Energy Survey Year-5. They're different from each other. They're not independent. They have some overlap in objects, so you can combine them all. You have to do one or the other or the other. And given, trying out those three possibilities, you get significance against lambda CDM. That's 2.8 sigma, or 3.8 sigma, or 4.2 sigma, depending on which supernova data set you combine with DESI and microwave background. So this is quite exciting. This got a lot of publicity and was very much talked about result in cosmology. Probably the most talked about result right now in cosmology is this result, which we saw in DR1, and now we are seeing and confirming with better precision in DR2. We've been trying to understand it. I can say a lot more about this, but I won't in the interest of time. I will just say it's exciting to see this development. Some hints away from lambda CDM that are, we call them, sorry about it, we call them tantalizing hints. We don't have like a proof, but they range between about 3 to 4 sigma. And so we have a whole dedicated paper from DESI on this subject. And in that paper, we do many other parameterizations that are not W0 WA. What's remarkable to me is that we actually find results that agree with the standard parameterization. So equation of state W in the best fit W0 WA model looks like the green curve. So the green curve is the best fit results from DESI. So the dashed curve is the standard lambda CDM model. The green curve is the model that had the so-called phantom less than -1 equation of state in the past, where it crossed to greater than -1. And it's a weird model because when W is less than -1, dark energy density increases in time. So it's actually density, joules per cubic meter, that's increasing in time. It's weird, allowed, but weird. And then it crosses the phantom here, and then it goes to maybe more regular case when energy density is decreasing in time. While in the standard model, dark energy density is constant in time. And you can see that this other different parameterization with bin W has bigger error bars, but basically agrees with W0 WA. And we have many other parameterizations here, and I had independent paper with my student, which I won't talk about in the interest of time. We found that this W0 WA result is quite robust with respect to parameterization. So it's not that like we use the wrong parameterization. No, the data really do want something like this. Why the data want something like that is a big question to which nobody in the world knows the answer to that right now. Even asking what in the data is pulling away, it is surprisingly hard to answer. It's not any one data point. It's not any one of those measurements. It's a more complex combination of things in the data that pulls away from lambda. Okay, so that's just covering a tiny bit about what's a very active topic in cosmology right now, trying to understand these results and really being excited about this anomaly that we are seeing at 3 to 4 sigma. So in conclusion, dark energy is premier mystery in physics and cosmology. And I mentioned in passing some of the forthcoming observations. We've seen Hubble tension. That's really exciting. And now we see this dark energy anomaly. That's really in my mind, two exciting things that might be hinting at something that might need a theoretical explanation. In addition to dark energy, I mentioned two other featured results from DESI Year-3, measurement of the Hubble constant, and very, very tight limit on some of the neutrino masses. More things are happening soon from other surveys, but from DESI, what we call full shape analysis. So analysis that goes beyond the BAO peak and really measures the clustering of the full clustering signal of galaxies. Higher order statistics, that means going beyond the power spectrum, but looking at other measures of clustering by spectrum, machine learning methods, all kinds of different things. And then there will be more DESI data. There's going to be extension of DESI called DESI-2. Next decade, I hope I'm alive. Maybe the decade, who knows? I hope funding is good. SPEC S5, this is a next generation survey for baryon acoustic oscillations. And of course, there are data coming from Euclid and Roman telescopes and LSST. So it's going to be really exciting to see how these two developments, Hubble tension and the dark energy anomaly, how they vary in the near future. That's all I have for the moment. Maybe I can leave some time for questions, so I will stop here. Thank you.
Thank you.
Yeah, I have a question. Sorry. Can you comment a little bit?
Thank you very much,
on this?
Dragan. Now it's time for question.
Sorry. Yeah. So can you comment a little bit on this assumption that W is a linear function of the scale factor A that you made? You said that you didn't have time to explain, but maybe you can say a bit more about it.
Yes, I can. I'm not going to show any slides for that because I don't think they're necessary. So if you might say I like to have very rich, very flexible description of W, but the constraints are going to be terrible. If you have even more than 2 parameters, the constraints become very bad very rapidly because W as a function of time is very challenging to constrain. So you need to strike a balance between relatively few parameters and so that you can get constraint and flexibility. And this W0 WA parameterization does strike that balance. It's only 2 parameters for W, and it's been shown to fit many models. However, if results were only based on that assumption, you'd be suspicious. But as I mentioned in the Loda paper, as well as other independent work, many other parameterizations have been tried. And sometimes you get bigger error bars, but you do find the same kind of result. So you don't need this parameterization. You can take some other parameterization, and you should be seeing disagreement with lambda CDM at a comparable level. It doesn't depend on that parameterization.
Is there a parameterization independent, an assumption independent way to extract constraints, or you always need some kind of assumption?
No, there isn't. This leads me to I have a little rant about the word model independent. I hate that word, model independent, because things are never model independent. For sure not. You always need a model. And even people say they don't have a model, they have some kind of spline or machine or Gaussian process. There's always some kind of smoothing involved. So even if you start with many parameters, you need some kind of smoothing of the equation of state. And when you imply that smoothing, that's a model. So you always need a model. You cannot be model independent completely. But what makes me feel a lot better is that things don't depend on this parameterization. You can take many others and you get similar results.
Okay, thank you.
Thank you. Other questions? I would have one very, let's say, not complicated question. You presented us a lot of results, in particular about omega, but can you translate it into the language of the lambda constant? Can we say now that we really know, and with what, let's say, sigma, we know the current value of lambda, and do we know much about how much it was constant? I mean, does it evolve in time or not?
Yeah, no, we either know or don't know, but this can be answered for sure. So current value, we don't know anything about current value because we look in the past, right? We look at those galaxies in the past. So we know the value a few billion years ago. We don't know literally anything about current value today, right? So, but this is true in astronomy in general, right? We don't know anything about the sun right now. We know about the sun 8 minutes ago. So it's the same kind of thing. So we know, now you can ask, do we know anything about lambda? So the lambda, the parameter you like, that's been increasing with time and then decreasing with time. It's weird. So energy density, the physical thing, corresponding to this W has been increasing with time and decreasing in time. You can convert it to physical units, but it's going to be the usual comparable number, whatever it comes out to be. And we measure it best at redshift about 1/2. So at redshift of 1/2, we have the best measurement of W and therefore the best measurement of lambda. So I think we have the answer to all that. And those numbers are maybe not so interesting. They are, whatever. Yeah.
Can you add a very short question? Do we know something more precise about the time when universe start to accelerate, or it's almost the same as it was found by Rees and these groups in 1998?
Yeah, that's a good question. It's hard because we have a global statement about the model that disagrees with standard model. But now if you ask, do we know anything about this time or that time, we have a lot less statistical power. So I think the answer is no, we don't know anything exactly about that time. What we are seeing evidence for is this dark energy, and again, density increasing and then maybe decreasing with time. But if you ask The time the dark energy started is a comparable as originally seen. So the big picture of dark energy is all the same. You know, it started 5 billion years ago, at redshift of a half, universe started to accelerate. The thing that's different is the dark energy density now appears to be changing in time. While in the standard model, it's constant. Raw dark energy is constant in time.
Thank you.
Right, so, yeah.
Other questions?
May I?
Yes.
Thank you for a very interesting talk. I'm a layman in this field, but still I have a question for you, if I may. Somewhere you mentioned baryons decoupled from photons, which puzzled me. Does it mean that baryons do not interact to the photons, or what else?
Yeah, that's a famous process of recombination that happened 300,000 years after the Big Bang. So the key thing is that protons and electrons were separated. And so photons they were coupled by Coulomb force, and photons and electrons were scattering in the Thomson process. So photons and electrons scatter. But what happened at recombination is electrons and protons combined into hydrogen. And when electrons and protons combine into hydrogen, then photons have nothing to hit anymore. The cross-section with hydrogen is much smaller. So then photons just free stream, they just travel. So prior to that time, they were bouncing off electrons, and then electrons disappear, they combine into atoms, and then photons just free stream. So that's the change that happens fairly suddenly at the redshift of 1,000, 300,000 years after the Big Bang. And that changes everything. That changes in particular the speed of sound. So photons after that time, they just travel in straight line with the speed of light. But prior to that, they are kicking electrons.
Okay, still, what about the excitation and the de-excitation of the atoms? They seem to produce or to absorb light. What about that process in the picture you have just described?
Okay, good question. I don't know the exact answer, but I think the probability for that is much lower than probability for scattering with a free electron. So I think the probability for photon exciting a hydrogen atom is much lower than photon hitting an electron. And I think it's all about the probabilities. So I think that's a negligible, much smaller probability.
Okay,
it happens, but not so frequently.
Yeah, I see. Thank you.
I think, Dragan, that the energy of the photons after the decoupling is so low or much lower, so the probability of exciting the electron is very low.
Yeah, you're right. Yeah, that's right. That also makes sense. Yes, the energy is too low. It's less than an electron volt. It's some fraction of electron volt, so it's too low to excite. Yeah, good point.
Nevertheless, I have to add, quantum optics deals with such processes, and there are no real photons at all. That is coupling between not the total hydrogen atom, for instance, but of the internal degrees of freedom with the vacuum, quantum vacuum fluctuations, which are just virtual processes. So somewhere in that picture, I would, as I have already told, I'm completely layman in this field, I would somewhat worry about this possible role of the vacuum, which might be everything but not that.
Yeah, I don't know the answer to that, unfortunately. I see what you're saying. Vacuum fluctuation, again, that exists, but it's a totally negligible effect at the time I mentioned, but I'm not exactly sure why. I'm not sure I understand it fully.
Yes, I realized your idea. Thank you very much.
Professor Dmitrievich, any question?
Yes. As I understood, you collect and study dark energy, right, Dragan? Yes?
Yes, well, we look at the signature of dark energy in the clustering of galaxies.
Okay, and what about dark matter? I didn't understand.
Oh, yeah, dark matter is there. So we constrain that omega matter parameter represents dark matter mostly. So we constrain dark matter and dark energy together, and so dark matter is in that power spectrum is all about dark matter. So dark matter is a completely major part of modeling. So in the modeling, you have dark matter and dark energy. And I emphasize constraints on dark energy, but that first number I showed was the number on omega matter, right? So I don't know if you can.
Okay.
Yeah.
So my question is, did you find something? Did you find some suspicious similarity between dark matter and dark energy?
No, that's a long-standing. You might think, well, both have the similar name. They're both wise. They're not one. They are so different from each other that nobody succeeded in connecting them. This is not just DESI data. This is correct. The reason is dark matter clumps like matter. It's very clumpy, and dark energy is very smooth and pushes away. And these two behaviors are so different that no success has been made in kind of making one fluid, one kind of thing that does two things, because these two things are very, very different. And so it's very interesting. You might say, well, there might be just one dark component, but if you try to build a model as one dark component, it separates into two parts, dark matter and dark energy, because they're really very different from each other. It's because of this equation of state, W, which is 0 for dark matter, which is close to -1 for dark energy.
Yeah, so this, I should say, very old statement is still true, right? Dark matter is completely different than dark energy, right?
Yeah, for sure. For sure, that's true. We don't know what dark matter is. We know it's 30% of the budget. We now have DESI numbers. We've known that already. We see no departure from the known behavior of dark matter. It's still a great fit to the data. It's the dark energy that we are seeing some, surprises. But we definitely constrain dark matter along with dark energy. That's mandatory. That comes, and that's this omega matter number.
Okay, thank you.
I don't see any other hand or request for a question, so it's exactly 1 hour and I think 2 minutes as we start. So Dragan, thank you very much. It was very inspirative, I think, very nice and a very good review. So keep in touch, and I hope we will see in Bucharest with most of the students, and I hope there will be another chance for us to have your talk in the future. We will stay in touch, and I wish you all the best, and all the best to all in the auditorium. Have a nice rest of the day, and see you.
Thank you, Goran, and thank you, everyone. It's been a pleasure.
And Dragan, please bring one book with you in Bucharest.
I will. Yes, I will bring. Good point. Will do. With pleasure. Thank you.
Thank you.
Take care.
Thank you.